What's the most thing?
The most time-consuming problems were the ones we probably just finished. Those Simpsons rules and trapezoid rules. Some of those take forever. They're not difficult, they're just time-consuming. The ones that require the most thought that we've done are all those application problems, related rates, optimization.
Those other one was difficult.
Require a lot of thought. So here's
the second derivative of all those trig functions.
Yeah, those are pretty tough.
Those were tough.
Amen. One time we had to do a quiz.
So,
that was crazy.
We've got to develop.
It was by hand on a test with you. I think I'm the second third.
And use properties of the natural log. And we're going to pair that with the number e. And then we're going to find the derivative of natural logarithmic functions. You guys learned about natural log in Algebra 2, and then you learned about it again back in pre-calculus. So I know you already know a lot about natural log. That's good. You're going to need it. Just a little bit of quick background, though. This is probably how it was defined to you back in pre-calculus, the natural log. So if you started with this function, y equals e to the x, obviously that's not a logarithmic function, right? It's an exponential, right? But you were taught in pre-calculus how to find the inverse of any function, not just exponentials. How do you find the inverse of any function?
You switch the y and the x.
You switch the y and the x. And then we're going to have to use a logarithm. So the inverse is going to be x equals e to the y. But this isn't a function in terms of x. Right now, this is a function in terms of y. So we want to switch this so we have a function in terms of x. So what would the next step here be?
You've got to log both sides.
Which particular logarithm?
Log base e.
Which is?
The natural log.
Natural log.
To the bottom.
So when you learned this in pre-calculus, you learned that the natural log was just the inverse of e to the x. Does this sound familiar?
Yep.
This is way back in the 17th century, 16th century. This actually is how the natural logarithm was developed. Definition of the natural log. This is going to look now more familiar from a calculus perspective. This should look familiar from a pre-calculus. The natural log of x is equal to the integral from 1 to x of 1 over t dt, and x has to be greater than 0.
That doesn't make any sense. That's all hogwash.
Let me show you something here. What if Okay, you guys, this is actually a very, very important definition.
Gibberish.
Try this.
Rubbish. Diddle.
Try that.
Bothersome.
Go. Try it.
I tried it. I tried. Oh, I know this one.
What is it?
It's what? One.
Yeah.
No, I didn't.
Anybody got it? Come on, this is easy.
Second.
It's a simple integral, 1 over x dx.
Minus 1.
No problems at all, right?
No, there's a. It creates a problem.
Is there a problem?
There is a problem.
Keep going.
So hopefully by now you've tried this. But if you try to increase the exponent, what would it become?
0.
But then you'd have to divide by 0. So you guys, hey, rather than saying, well, this integral just doesn't exist, rather than saying that, mathematicians hundreds and hundreds of years ago developed a new function so that this integral could become possible. Isn't that what this is? The integral of 1 over t dt? Didn't we just try to take the integral of that? Okay. It wasn't possible using traditional integration techniques. Okay. That's how the natural logarithm has been defined so that this integral becomes possible. Okay. That's all that means. And by the way, where this is leading, I'm kind of skipping ahead. You guys ready? Kind of skipping ahead to the end of the lesson here, but we might as well talk about it now. If I took the derivative of this, wouldn't I have to take the derivative of this also?
Yeah. You would.
So does this look familiar to anybody?
Now it does.
Looks like what we just learned about. Now we know.
Keep going.
Looks like it's going
The second fundamental theorem of calculus, right? If you take the derivative of an integral from a constant to x, don't you essentially just replace the t with x? So what this leads to is the definition of the derivative of the natural log. It's just 1 over x. Okay? But that's later on in the lesson. So, just a couple of quick properties that you hopefully remember from pre-calculus. Properties of logarithms. You have to use these properties in today's homework, otherwise it's going to be very difficult. By the way, these properties apply to all logarithms, not just the natural logarithm. But since we're studying the natural logarithm in this section, we're just going to apply these properties to the natural logarithm. That's a to the power of n. These properties looking at all familiar from last year? Which one do you remember of these four?
LN1.
What does it equal? So you don't remember it then?
I recognize.
Nobody? Come on, you guys. Think.
Wait, what?
What do all of these equal?
Oh, I know. Wait, what? Oh, they don't all equal the same thing.
They don't all equal the same thing. They all equal different things.
Okay, the ln of the log of 1 is, I know this.
The base here is e.
Yeah, but I know it's of 1 is equals
It's just 0.
0.
Okay. The natural log of 1 is always equal to 0. The log base 2 of 1 is equal to any logarithm. If you're taking the logarithm of 1, it always equals 0. Okay? Just something you learned last year. There's a really easy explanation. What's the base of the natural log? So there's really a hidden e right there, right? What's e to the power of 0?
0. 1.
Anything to a power of 0 is 1, right? E to the 0 is equal to 1. That's what. The natural log of A times B, this is the product property of that. It's plus. Now, natural log of A plus, natural log of B, is this looking more familiar now?
Yeah.
Let's skip property 3, let's go down to property 4. Knowing property 2, what's property 4 going to be?
ln A minus ln B.
Natural log of A minus natural log of B, good. And then the natural log only cancels a base of E. This is a base of A, so these aren't going to cross out. But you did learn this last year. What can you do with this power?
You put it in front of the ln.
Move it down to the front. So this is n times the natural log of A. Those 4 properties you're going to have to use in today's lesson. Okay.
I'm excited because I remember these properties.
So, just a quick example of what you're going to have to be doing later on. Let's see how you handle a few of these. Expand. Natural log of the square root of 3x plus 2. And expand.
You just barely got them. What? Wow, that was a really large jump.
Wow.
Yes.
I don't know about that.
Thanks for gradually getting us into this.
And just easing you into it here.
Yeah, that was very kind of you.
You eased into it last year. Now you're just being thrown into the fire.
Yes, we are.
I hate fire. Fire.
We're doing A and B. Start with A. A is a tad bit simpler.
Okay, that was
Now,
a little better.
if I haven't mentioned it yet this year, I know I mentioned it a ton last year, if you had me last year. Logarithms and radicals don't play nicely together. Logarithms and radicals do not play nicely.
How did they play?
So always switch radicals to exponents. Always. If you're dealing with logarithms and you see radicals, always switch those to exponents. So the first thing I would do is write this as the natural log of 3x plus 2 to what power? Now there's just one step left.
That's the easiest step of them all.
Move the 1/2 down in front. So it's 1/2 times the natural log of 3x plus 2. You cannot, you guys listen, you cannot expand the rest of this. Because it's adding. If it was 3x times 4y or something like that, then you could expand it. This one's a little more challenging. It looks like it's a lot more challenging, but it really isn't. There's a product rule in there somewhere. There's also a quotient rule in here, right? First thing I would deal with is your quotient. You have a numerator and a denominator. So Hayden, how would you expand a quotient? Yeah, Hayden.
I do know that ln of A was something so I turned to ln of A minus just the
Okay, so natural log of minus the natural log. And I'm going to go ahead and change that cube root into. Go ahead and change that. So Gabe, what is this right here?
This is chain product rule.
So we have x times x squared plus 1 to the 1/3. Isn't that a product rule?
You're going to have to add.
So can we further expand this?
Yes, we should.
Yeah, because there's a product inside here. So I would further expand into 2 more logarithms. You're going to have a total of 3. So now you have a total of 3 logarithms. Look exactly at what you have written compared to what I have written.
Look back. Now look.
Are you noticing my minus sign, thinking I made a mistake?
Yeah. No, because they're minusing both.
Aren't you supposed to subtract the entire expansion? So you've got to remember, that's a common mistake, you guys, common mistake. Or you can keep those in parentheses and make it plus if you want.
Okay, that makes sense.
Okay, it's up to you. Either you keep the expansion in parentheses and you make it a plus, or you distribute the minus sign and don't have parentheses. It's up to you. There's only one more thing to do. Move the 1/3 down and the 2. So this really wasn't as bad as it looks.
You're right, I guess.
Always. Okay. So here's where this is leading. I know I'm moving pretty quick. I'm sorry, but this is all just old stuff, right? Here's the new stuff. Okay. This is the last topic. We're already on the last topic.
Oh my
Whoa,
God.
that was
The derivative of the natural log function. I already kind of showed you that the natural log was defined as the integral from 1 to x of 1 over t dt. That's how we defined it back at the beginning of the lesson. Right? If we now take a derivative with respect to x on both sides, then this right here is just an application of the second fundamental theorem of calculus. If you're taking the derivative of an integral from a constant to x, do you remember what happens here? The x replaces the t. So the derivative of the natural log of x is equal to 1 over x. And it must be true that x is greater than 0. You can't take the logarithm of negative numbers. You might remember that from last year.
Yeah.
your applause cannot be negative. Right? It's called an applause.
It's inside.
Yeah.
That's good news. The second property,
This guy right here. It's on the roll.
you guys, the second part of this is a chain rule. What if you're taking the derivative of the natural log of u, where u represents another function? Use property 1. Let's see if you guys can figure it out. Think of inside and outside functions. The natural log is the outside function. What's the derivative of natural log?
1 over.
It would be 1 over u.
du dx.
But now you've got to take the derivative of the inside function, which is
Oh yeah. So it's kind of like
it is implicit.
implicit.
That's exactly what the chain rule is. It's
Okay.
kind of like implicit differentiation.
Oh, sweet.
Now, most textbooks have a slightly different notation. Du dx. Would you guys be okay if we call that u prime?
Okay.
You all right with that?
Yeah.
So other textbooks have this notation: u prime over u. U prime is the same as du dx. And this also must be true here that u is greater than 0. So these ones we're going to kind of ease our way into. I'm not going to start with a super hard one yet. Okay, you guys ready?
I'm ready.
Starting with some more simple ones.
What's the log of a constant other than 1? Does it vary?
It varies, yeah. So it's like the square root of a constant. It just depends on the constant.
Okay. So, would the derivative of ln u represent the derivative of the constant of the log?
No, because u right here isn't representing a constant. U represents a function.
Okay, it represents like the x squared plus 1.
Or 2a.
Oh, yeah. So, okay. Gotcha.
Now, I know we're dealing with a new function. I can sense a little bit of unease, possibly, but let me show you something that you could all probably do in about 5 seconds. You ready?
Okay.
If I ask you to take the integral, or sorry, the derivative of that,
X to the 1, negative 1.
how'd you take the derivative of that? Drop down the 1/2, subtract 1, but isn't there a chain rule? So those will cancel out, so it's just 1 over the square root of 2x. You guys are pretty good with the chain rule, aren't you? That's all that's happening here. Forget about what's inside. What's the derivative of the natural log?
That's what we're doing.
It's 1 over whatever was there to begin with, right? But now you have to do a chain rule. What's the derivative of what was inside there to begin with? So then you multiply it by 2. So the derivative is just 1 over x. If it's a constant times x. Yeah.
That means the derivative of ln 2 equals 0.
Yeah.
Is that the same with every constant?
ln of 2 is just a constant.
Oh.
The derivative of a constant is always 0.
Sweet.
Yeah,
Okay.
it's a good thought. What about this one, you guys? We gotta speed this up. We have a few more challenging exams coming up. 1 over x squared plus 1 times 2x, because this is the derivative of the inside function. So this is just 2x over x squared plus 1. You following now? What's going to happen here? Yep, the product rule of derivatives.
So it's x.
So if we're thinking like this is f and this is g, then the product rule is f prime times g plus f times g prime. That's the product rule. So what's f prime? 1. And then you multiply that by g, the natural log of x, plus now we have x times g prime. What's the derivative of natural log of x?
1 over x.
1 over x.
Well, x times 1 over x is 1. And then 1 times ln x is just ln x.
So it's natural log of x plus
1.
1. That's your answer.
Oh, wow. Hey, that's simplified. Simplified quite nicely. Simplified.
Okay, part D. Oh, I see what you're saying. Not quite. That's a good idea, but not quite. This is a chain rule, but you have to be careful on what you're calling the outer function, what you're calling the inner function. What's the outer function? Something to a power of 3. So that's what we take care of first. How do you take a derivative of something to a power of 3?
So it's 3.
So it's 3 times the inner function, then decrease it. Now you take the derivative of the inside function.
1 over x.
Yeah.
This is fun.
If there was a constant.
You want to have a study group party? This is
Yeah, if there was another, hey, that's a good question, you guys. If there was something inside here, hey, if there was something inside here, like 3x to the third or something weird, wouldn't that be another chain rule, if that were the case? Double chain. Anyway, that's not the case here. So it's 3 times the natural log of x squared all over x. Okay. Well, we're kind of jumping into some
fun stuff.
challenging problems, I guess I would say. This one would be pretty challenging.
Oh, good. That kid is here. There's a lot more fights in junior jazz games.
This is 2x to the third.
Just where, like, just compact.
All right, let's discuss. Now, you guys, as it is, we're taking the natural log of some kind of weird function. Kind of like we were doing on part A or B, all we did is 1 over that function times the derivative of that function. But you would agree this function is a little more complicated? Yeah, so your task is to find f prime. So we just spent a few minutes talking about properties of logarithms. If you can expand this all into separate logarithms, it's going to be much easier to take. Am I interrupting you guys? If we can expand this into separate logarithms, it's going to be much easier to take the derivative. Okay, so before even bothering with the derivative, expand this natural logarithm into multiple logarithms. Well, no, we're not even taking a derivative yet. We're just going to expand this. So expand the natural log of, just using those basic properties of logarithms we talked about at the beginning. So the first thing you take care of is the quotient. It's the natural log of the numerator minus the natural log of the denominator. And then we can split the first one up into 2 more logarithms because it's a product property.
We have kind of derivative all of them. After you drop the 1/3 and 2 in front.
And then drop down some powers. Oh, sorry. 1/2. Yep, it's a square root. Oh, thank you.
Sweet. Ln x is 1 over x. Plus.
So now it's fully expanded. This is what f of x equals. Now you can take the derivative of each one individually. Does that seem a little bit easier?
Yeah.
Than what we started with?
Yeah.
Mhm. So, what's the derivative of just natural log of x? Now, this 2 in front, when you're taking the derivative and there's a constant multiple, You just take that out of the derivative process and remember to multiply it at the end. So,
Okay.
what's the derivative of natural log of x squared plus 1?
It's 1 over x squared plus 1 times 2x.
Okay. Then we subtract 1/2. So, and then we multiply that by 1 over 2x to the third minus 1. But then we multiply that by the chain rule. 6x squared. Okay. So we have 1 over x plus 4x over x squared plus 1 minus what are we subtracting?
6x squared over 4x.
I just canceled the 1/2 with that 6 and made a 3 out of it. You guys alright with it? No, because this x is part of that term, 2x to the third minus 1.
I genuinely enjoyed that.
Yeah, just leave it like that.
Yeah.
Do with it. I can do it.
Is that what
This is 2x to the third minus 1. That's x squared plus 1. Okay. Now, just a little side note here before we leave. You guys just want to write this down if you happen to see it in your homework so you're not confused. We already decided this was true, right?
Yeah. Why I?
Or even if we change it to a u, the natural log of u is 1 over u times du, or u prime. Sometimes when you're taking the natural log of something, you do end up having to take the natural log of negative values, which doesn't work. So quite often they put absolute value. In case u is negative, they put it in absolute value. Right, Gabe? Because what happens if u is negative but it's inside an absolute value? And then you can take the natural log of it, right?
Yeah, absolutely.
So that doesn't change the derivative, though. Even if it's inside an absolute value, it's still u prime over u. Okay? It's the same derivative. Even if the expression's inside an absolute value, the derivative is still u prime over u. Yeah. So not tomorrow. Next time, when? Thursday, Monday? What is today?
Friday.
Okay, guys. Tuesdays.
ACT testing.